New laboratory experiments are working to produce that color and others found in Jupiter's stormy cloud tops here on Earth, and researchers have found that radiation and temperature play key roles in changing the color of some of the transparent material found in the clouds. A primary suspect in coloring Jupiter's clouds is ammonium hydrosulfide, a type of salt. Formed by ionized ammonium and bisulfide, it quickly decomposes at typical atmospheric conditions and temperatures on Earth, making it challenging to investigate its properties. Models predict that ammonium hydrosulfide is the third most abundant cloud component on Jupiter, behind ammonia and water, Mark Loeffler, an astrochemist at Northern Arizona University, told Space. After hitting the salt with simulated cosmic rays, they compared them to observations made by NASA's Hubble Space Telescope. This work took a bit because there is not much published on this compound, and there appeared to be a lot going on in the sample, Loeffler said. In recent years, the storm has shrunk to the width of a single Earth. Previously, it was estimated to be 3 Earths wide. At the same time, observations showed that the color of the spot has been changing, suggesting that its composition may also be shifting. Though ammonium hydrosulfide is present in Jupiter's atmosphere, Loeffler said, it doesn't exist as a gas. Instead, it must be condensed as grains of salt that are mixed with or coat another material. By itself, ammonium hydrosulfide is transparent and colorless. But in Jupiter's clouds, the salt doesn't sit in isolation. These rays, which come from outside the solar system and even outside the Milky Way galaxy, can change the color of many salts, as previous experiments have revealed. To determine how ammonium hydrosulfide reacted to radiation, Loeffler and Hudson first had to cool the sample holder to temperatures where the salt would remain stable as a solid. Then, they sprayed ionized ammonia and hydrogen sulfide into the sample holder, where the two components reacted to produce the salt. Next, the researchers used a particle accelerator to bombard the sample holder with protons to represent cosmic rays impacting the cloud. Throughout the process, the researchers monitored the ice and collected images in both visible and ultraviolet light. Loeffler summed up the process in a single word: fun. The researchers found that varying the temperature of the cosmic rays affected the color of the salt. At low temperatures of -263 degrees Celsius, -505 degrees Fahrenheit, and -223 degrees centigrade, -370 degrees Fahrenheit, the salts became orange or reddish-orange. At higher temperatures of -153 degrees centigrade, -244 degrees Fahrenheit, and -113 degrees centigrade, -172 degrees Fahrenheit, the salts turned green. The researchers attributed that greenish tint to sulfur. Only a small fraction of sulfur has been identified in the clouds, however, at smaller ratios than those found in the salts produced in the lab. It would be nice if the red colors we see at low temperatures could be responsible for the Great Red Spot, but those are probably too cold, Loeffler said. So what role does ammonium hydrosulfide play in coloring Jupiter's legendary storm? The researchers still aren't certain. The visible color of the ammonium hydrosulfide, whether red or green, or something in between, is determined by the wavelength of light that the compound emits, but the full profile of light coming from the compound includes wavelengths beyond just that visible range. Although the ammonium hydrosulfide ice at low doses and low temperatures makes a reasonable match to what has been observed on the planet at some wavelengths, it doesn't match all the wavelengths scientists have seen in Jupiter's storms. Ices irradiated at higher temperatures make a better overall match, but the wavelengths that create the greenish color are obviously a mismatch with what Hubble has seen. After comparison with this new low-temperature data, it seems evident that the best fit of a single ammonium sulfide ice is one that has been irradiated and warmed up to higher temperatures so as to remove the sulfur radical, the researchers said. That study, along with another paper from 1976, focused on only a single temperature when the sample was irradiated. Along with the new research, which will appear in the March 1 issue of the journal Icarus, these are the only papers that report the results of laboratory work on ammonium hydrosulfide, according to the authors of the new study. That's because the instability of the salt makes it a challenge to work with, Loeffler said. Even worse, he said, the samples destroy lab components. It really is not the best material to work with, Loeffler said. But that doesn't deter the scientists. Now that they've studied how ammonium hydrosulfide changes over a range of doses and temperatures. The pair plans to include other compounds in their experiments that could contribute to the coloring of the Great Red Spot.